Hello again. We're continuing our discussion of improper integrals by talking about just that. So the last lesson was meant to lead up to this lesson. All right, so let's get started. Normally when I have a definite integral, there's a start point A and an end point B, and we've all seen that notation before. But what would happen if the integral actually had no endpoint? It went on forever. That top point went on to positive infinity. Well, that's what an improper integral is. So what's going to happen is, remember, that integral represents the area under f of x. So sometimes that area will be infinite. It'll go on forever as well, but sometimes it'll actually converge and be a number. So how do we know which is the case? Well, what I do is I leave the endpoint as it was, as b, but I find the limit as b goes off to infinity. All right, so if that limit actually exists as a constant, then the integral is convergent, but if not, then the integral is said to be divergent. All right, let's look at a couple of examples to see what we mean. The first one is going to be an exponential example, and the second one is going to be a polynomial example. So I'm looking at the integral from 0 to infinity of e to the negative 3x. So I change that infinity to a b, and I take the limit as b goes off to infinity. Okay, so first I'm going to find the integral, take the antiderivative of e to the negative 3x, and plug in b, plug in 0. The antiderivative of e to the negative 3x is negative 1/3 e to the negative 3x. So if I plug in b into that and I plug 0 into that, this is what I get. I notice that e to the 0 is 1, so that makes the second term just 1/3. Now I'm ready to take the limit as b goes off to infinity. Well, as b goes off to infinity, e to the negative 3b is going to get really, really small until it approaches 0. So that first term is going to approach 0. The second one will stay at 1/3. So the limit is 1/3. That means the limit exists and that integral is convergent. All right. Now let's look at one that is more of an x to the n, specifically an x to the negative n situation. I'm going to take the integral from x equals 2 to x equals infinity of x to the negative 5. All right, I'm going to rewrite it using the limit instead. So it goes from 2 to b, and I let b go off to infinity. So first I integrate from 2 to b. And the antiderivative of x to the negative 5 is going to be negative 1/4 x to the negative 4. I'm going to plug b into that, I'm going to plug 2 into that, and those are the two terms I get. If I simplify the last term, which is just numbers, I'll get 1 over 64, and the first term will stay as it is. So now I'm ready to find the limit as b goes off to infinity. Well, as b goes off to infinity, b to the negative 4 is going to get really, really, really small until it approaches 0. But the 1/64th will stay as 1/64th, so that is my answer, 1/64th. So again, the integral converges because the limit actually exists. All right, so what if we had a function that was more difficult to integrate? So there's kind of a trick I can use. I now know that the improper integrals of e to the negative x and x to the negative p, those converge. Those were my two examples that I just showed you. So if I have a function that's hard to integrate, but I know that it's consistently less than one of those, then I know that that function will converge, because that function lies entirely underneath those functions, and I know those functions have a limited area underneath them, so something that is a smaller function is also going to converge as well. All right, so let's look at this example, x to the 1/3 over 1 plus x squared. I'm not sure what the antiderivative of that is, but what I do know is I know that that denominator, 1 plus x squared, is always going to be bigger than x squared by exactly 1. So if that's on the denominator, and I've actually made the denominator smaller, that's going to make a function that is bigger. So I've got x to the 1/3 over x squared. So what I can do is I can rewrite x to the 1/3 over x to the 2 as x to the negative 5/3. And that is in the form x to the negative p. So I know that x to the negative 5/3 will converge. We've shown that any integral of x to the negative something is going to converge. And since I have a function, I'm using a function that's actually less than that, I know that that's always going to converge as well. All right, so kind of a tricky thing to do, but it works, and it's valid. All right, here's another example of that. Okay, so I want you to notice something, and it might be obvious, but if not, I can explain it during class. If the absolute value of a function, when integrated from a to infinity, if that converges, then if I take those absolute values away, then the function actually converges as well. All right, so let's say I have sine of x over 1 plus x to the fourth, okay, and I need to show that that converges. Well, I know that the absolute value of sine x is less than or equal to 1 for all x's. So what I can do, I also know that the absolute value of 1 plus x to the fourth is bigger than x to the fourth for all x's. I didn't even need that equal sign on the bottom, so it's actually strictly greater than. So I know that the function I was given, the absolute value of the function I was given, is always going to be less than or equal to 1 over x to the fourth. I know that 1 over x to the fourth, which is basically x to the negative 4, I know that that converges, so I know that this function, the absolute value of the function that I was given, I know that that converges as well because it's always going to be less than 1 over x to the fourth. So, based on that point that I've written in blue up at the top, since the absolute value of that integrand converges from 1 to infinity, then the original one converges as well. All right, so once we know that an integral converges, we can actually find the value of it using integration techniques. Okay, so now we actually have to know how to find the integral. It's one thing to show that it converges, but now we need to show what it converges to. So let's take this example here. I've got the integral from 1 to infinity of x times e to the negative x dx. I'm going to change that to a limit by changing infinity to b and finding the limit as b goes off to infinity. So if I do integration by parts, which I talked about in a previous chapter, in a previous lesson, the antiderivative of that is going to be negative x e to the negative x minus e to the negative x. And if you're unsure as to how I got that, we can go over that in class as well, or you can always go back to the video on integration by parts. So what we get is the limit as b goes off to infinity of negative x e to the negative x minus e to the negative x. So I'm going to replace x with b, and then I'm going to replace x with 1, just like I would with any integration. And I get negative 2 times e to the negative 1 plus the limit as b goes off to infinity of 1 plus b all over e to the b. All right, so I don't know that limit offhand, but remember I can use L'Hopital's rule, which again was discussed in another previous lesson. And so I can take the derivative of the top with respect to b and I'll just get 1. And if I take the derivative of the bottom with respect to b, I'll get just e to the b again. And that limit I know is equal to 0 as b goes off to infinity. So that second term basically just goes away. It's equal to 0, so all I'm left with is negative 2e to the negative 1. So that's kind of a lot to absorb. I will understand if you have questions. So please let me know if you do have questions, and I will see you tomorrow.